two very long wires carrying the currents shown on the picture are oriented perpendicular to one another. We'd like to find the net magnetic field at points P and Q for two different cases. In case 1, the horizontal wire has current pointing to the right, and in case 2, the horizontal wire has current pointing in the opposite direction towards left. I have labeled the vertical wire as wire 1 and the horizontal wire as wire number 2. The net field at point Q will be the sum of the magnetic field created by wire 1 plus the magnetic field created by wire 2. Let's first determine the direction of each magnetic field vector. Now, wire 1 is vertical and the current flows upward. Align your right thumb upward following the direction of the current. On the left hand side of your thumb, which is the location of point Q, because Q is on the left hand side of the wire, your fingers are pointing towards you out of the page. So the direction of B1 is out of the page, which is the positive Z direction based on the coordinate frame that I have on the picture. On the other hand, let's take a look at the magnetic field created by wire 2. Now this is case 1, so the current flows towards right. Align your right thumb towards right. Above your thumb, your fingers are pointing towards you, which is out of the page as well. Why above your thumb? Because again, point Q is above wire number 2. So that's how we determine the direction, by looking at the direction of curling of our fingers above our thumb. That's towards us out of the page, which is again the positive Z direction. So the two magnetic field magnitudes will add up. Now let's determine the magnitude of each magnetic field vector. Our general formula for the magnetic field due to a wire at distance r is mu0 times I divided by 2 pi r, I being the current in the wire and r being the distance from the wire. So for B1, the current is 6 times I, and the distance between the wire 1 and point Q is 2 times D. For B2, on the other hand, the current has magnitude 5 times I, and the distance between point Q and wire number 2 is just D. We add the two expressions by finding a common denominator and then simplify, and we get 4 times mu0 I divided by pi times D in the positive Z direction for the net magnetic field at point Q. Now let's calculate the net field at point Q for case 2, where we have the current in wire 2 flowing towards left instead of flowing towards right. The only difference will be the direction of the magnetic field vector B2. So B2 will be pointing into the page instead of out of the page, which is the negative Z direction. So then in this final calculation, we're subtracting the magnitude of B2 from the magnitude of B1, and the final result will be different accordingly. The net magnetic field has magnitude mu0 I divided by pi times D, and it points in the negative Z direction. Now let's determine the net field at point P for case 1. We have again current in wire number 2 flowing towards right. Let's take a look at the direction of each magnetic field vector. The current in wire 1 is pointing up, so align your right thumb upward. On the right hand side of the wire, or on the right hand side of your thumb, your fingers are curling into the page. So the magnetic field vector points in the page. In other words, B1 is pointing into the page, which is the negative Z direction. How about B2? The current in wire 2 flows towards right. Align your right thumb to the right. Below your thumb, your fingers are curling into the page as well. So the magnetic field vector B2 is pointing into the page, which is also the negative z direction. So again, the magnitudes of vectors B1 and B2 will add up, and the net magnetic field vector will be pointing into the page in the negative z direction. Next, let's determine the magnitude of each magnetic field vector. The magnitudes of B1 and B2 are the same as before. We can see that there's some symmetry in this problem. So point P is also at distance 2D from wire 1, just like point Q. And the distance between point P and wire 2 is D, again similar to the case with point Q. So the distances are the same and the currents are also the same for each wire. We get the same magnitudes for B1 and B2. The only difference is that we get an overall negative sign in this case. So the net field at point P is equal to minus 4 times mu0 I divided by pi times d k hat, meaning the overall net magnetic field vector points in the negative z direction. Let's repeat our calculations for case 2. The current in wire 2 now flows towards left. The only thing that changes is the direction of the magnetic field vector B2. B1 is still pointing into the page, but B2 is now pointing out of the page. So I still have a negative sign in front of B1, but I have a positive sign in front of B2, and the magnitudes are still the same. So when we add these two expressions together, we get positive mu0 I divided by pi times d. And the overall magnetic field vector at point P points in the positive z direction out of the page.